Okay, everyone, let's talk more mechanics. So today we're going to talk about momentum and impulse. Alright, and if you just watched our previous video, surely you remember that last time we talked about forces. And we came up with basically 4 or 5 different things. Obviously, the first three are we came up with Newton's 3 laws of motion, which are inertia, uh, F equals ma, as well as net forces. Now, what we're going to do is we're basically going to build upon that by essentially stating some more quantities and also looking at how they're interrelated with each other. So we discovered last time that the force applied to an object is directly proportional to its mass as well as acceleration, and the acceleration of an object for a given amount of force is inversely proportional to its mass. In other words, if you have more mass, it's going to be harder to move. Now, we're going to define a new quantity today, and that's going to be called linear momentum, as you can see. Now, linear essentially means in a straight line, and the reason why we specify linear momentum is because we also have something called angular momentum, which is way outside the scope of the syllabus, so you don't have to worry about that. But just do note that it is linear momentum specifically, and maybe just not just any momentum. And here's how we define it. So we have P over here, which is the momentum, is equal to the object's mass times its velocity. So as you can see here, we have mass, and here we have velocity, and that's the momentum. Okay, and here's the thing with momentum. Unlike forces, it's slightly trickier to exactly define what it really means to you in the real world. The way I like to think about it is that momentum is essentially how much hitting power, or how strong an object is, or in other words, the ability of an object to accelerate another object when it collides with it, right? So let's look at a big ball, and we have an arrow indicating that it's traveling towards the right, and it collides with this little ball, okay? Now, if this ball is very heavy, let's say it's a bowling ball, right, with a momentum of, well, let's say it has m of 3 kgs and a velocity of 10 meters per second, okay? It's going to have a momentum of, well, we can work out the formula and we can say it has a momentum of 3 times 10, which equals 30 kilogram meters per second. And this is the unit that we use for momentum. So very important to remember, kilogram meters per second is the unit which we use, because it's just kilogram, which is mass, times velocity, which is meters per second. So it has a momentum of 30. Now this ball, let's say, weighs only 1 kilogram, and it has a velocity, because it's stationary, of 0. Okay? Its momentum is going to equal 0, because it's 1 times 0, so it equals 0. And then kg meters per second, which I'm just going to indicate with an apostrophe, because we don't need to write that out. Now, here's the thing. If you remember from Newton's laws, you'll know that momentum, we learned that each action has an equal and opposite reaction. Well, now, because we know what momentum is, we can essentially realize that the deeper meaning of that statement is that momentum in a given system is always conserved. What that means is, when this ball collides with a small ball, all of the momentum is conserved. It can go either of 2 ways. One, all the momentum will be transferred to here, so the momentum of this one will become 30, and this will become 0. Or what can happen is it'll split, so it'll become, let's say, 15 here, and then 15 here. Or it could be anywhere in the middle. What will not happen is, you'll have something crazy like you'll have 20 over here and 0 over here, which would mean that we lost some momentum. Now, because of this law, we know that the momentum in a system is always conserved. So that's very important to remember. So anytime you have, let's say, addition of momentum, you always have to remember your initial momentum must be equal to your final momentum. So what this means is m1 v1, which is basically the momentum in the start, must equal m2 v2 of the entire system. Okay, and that's very important to remember. So let's look at this. Event, for instance, right? So we already decided that 30 kilogram meters per second was the momentum of this one, and this one is 0. Now they collide, okay? And we decide in the question that all momentum is transferred, okay, to this ball. And then the question says, find the velocity, okay? So the momentum from this one goes all the way to this one, and now we want to see the velocity of this tiny little ball, okay? So we know now, okay, that the momentum in this system is 30 kilogram meters per second, okay? So m1, v1 plus m2, v2, sorry. What we can in fact do is we can call these quantities our initial velocity, because again we are dealing with mechanics. So instead of saying v, we can say u, okay, and then this becomes m2, so m1 v1 plus m2 v2, okay. Now we know that this equals 30, okay? And we know this equals 30. Both equal 30. But we also know that here, this one equals 0, right? This one. And then in the second part, this equals 0. So that makes our life a lot easier, because essentially now what happens is m1u1 equals m2v2. And so from that, we can essentially say, okay, 3, so we're just going to substitute that out now, okay? So we can say 3 times 10 equals, because that's the mass and that's the velocity, which is 10, like which we said over here, equals 1, because that's our mass, and then the velocity is the unknown. We don't know what that is, okay? So that's going to equal times v. And from there, it becomes very simple. We know the mass and we know the momentum here, so we say 30 over 1 equals v, because we just move it to the other side. So what we find is our velocity is nothing but 30 meters per second. It's as simple as that. And so that's how we deal with momentum and the conservation of momentum. Now, when we have that, we can also define a new quantity. Sorry, not a new quantity, I mean a relationship between momentum and forces. And if you have a sharp eye, maybe you've already noticed that acceleration is linked to velocity. And how is that so? Well, we know that acceleration is equal to the change in velocity in a given in a given amount of time. Yes, delta v over t. So now if we know that, we can essentially rearrange this formula so that we get F equals m, and then we substitute a for delta v over t. And what do we have here? That is very significant, because as you've noticed, this is momentum and this is m delta v. So we can actually write this out as F equals the change in momentum in a given amount of time, or rather the rate of change of momentum. And we'll write that over here. Force equals the rate of change of momentum. And that is very, very important. Okay? So this is incredibly important. So we have to remember that. Okay? Because what this essentially helps us do is, well, it helps us integrate velocity and acceleration, which isn't directly given to us with calculating the force. So if you, let's say, have suvat, right, and you don't know the acceleration, well, we already did suvat earlier, so you should know how to do that. But essentially, if you find out the velocity, you can find out the acceleration, and then you can find out the force. And similarly, if you know how much the momentum has changed by in a given amount of time, you know the force applied. So that's very important. So let's highlight some of the important ones. So first we have momentum, we have force, and of course we have this one, which is the conservation of momentum. So we have 3 new equations already. Now we're going to take it one step further, okay? And so just try and keep up here. And essentially what we're going to say is, well, F is the rate of change of momentum. Yeah, sure. But what if we just want to find, how much the momentum is going to change by? We just want to find the change of momentum. Well, all we do is, we do F, we bring over the T here, times T equals the change in momentum. Now, the thing to remember always, by the way, is that, well, although we put a delta over here, in like 99% of questions, it's just going to be talking about the change in velocity, because how many times can you add more mass to an object? Not that often, right? Most of the time, the questions are going to deal with the change in velocity, so really you can write it as this, but then there can be some situations, right? It's possible that where it'll be the change in, the mass or something, so that's why we just write it as that. And so anyway, now we have F times T equals the change in mv. And this is also a new equation, which we can call the impulse. So the change of momentum, the total change in momentum is defined as the impulse. Okay? And is the product of force times the amount of time it was applied. Okay? So now we have basically 4 new formulas which we've learned. Momentum, the conservation of momentum, which I'll write here, conservation of momentum. And finally, we have the rate of change of momentum, which is the change in momentum over a given amount of time, which is nothing but us rearranging F equals ma. So we substitute acceleration for the change in velocity in given amount of time, and we get delta mv over t. And then finally we have impulse, which is F times t, which we just remove this t, and we get the change in momentum. So that's the impulse, and it's the product of force times the amount of time it was applied. Alright, so because we run the risk of running this video a bit too long, I will end the video now, but upload a part 2 where we will solve all of these, a bunch of these practice problems here. So I'll see you in a bit.